In this video, I will sort of talk about some interpolation algorithm that I've been actually working on to to uh, to represent functions and its derivatives. Um, the reason for doing that is because sometimes we need to actually parameterize a certain interface with polynomials. For example, the location of the interface has to be sort of parameterized some way, right? And then not just the interface, but also any kind of function has to be parameterized. And then we have different choices for parameterizing a particular function. And here we are actually working on one-dimensional functions. So we need to actually find some way to parameterize a one-dimensional function, say u(r) here, right? And r goes from -1 to +1. If it's a different range, we can do a kind of a transform, linear transform to convert it to a different interval, right? But here, so you can come up with some kind of approximation, and then you can represent this approximated function as a summation over. Um, it's basically a linear superposition of this particular function, and this particular function p with a wiggle on top of it is something that's called a Lagrange polynomial, and it's a polynomial of R. And then we're doing this kind of weighted summation of Lagrange polynomials, and the weight is given by u n hat, right? And then the number of polynomials we're actually using, n goes from like 1 to capital NP. So how many polynomials we're using? It's NP polynomials, right? NP Lagrange polynomials. And then that's one of the representation, and this representation is called a modal. It's a modal representation. It's basically representing a particular function as a linear superposition of different modes, and here the modes are actually given by the Lagrange polynomial at the order of n subtract 1, right? And there's also another representation called a nodal representation, which is basically this kind of representation. It's also a linear superposition of some kind of a function of R, right? And this function is not a Lagrange polynomial, it's a Lagrangian interpolating polynomial, right? Lagrangian interpolating polynomial has quite a simple form, but the reason that people use it is because the weights used to multiply with the Lagrange polynomials is exactly the value of that function at those interpolating locations, Ri, right? So here for the modal representation, the coefficients, the weights, is not the function value. But here, if you are using the Lagrangian polynomial, interpolating polynomial, then the weights is actually the function value, right? So each representation has its own benefits and drawbacks, right? For this modal representation, the polynomial modes are actually orthonormal. So the Lagrange polynomials are actually orthonormal to each other. So they are kind of perpendicular, right? That's a good thing because that gives you the if you are actually sticking it into a differential equation, then the mass matrix is kind of a diagonal, right? But here the coefficients has a is not exactly the same as the function value. Here the coefficients are the function values, but the Lagrangian polynomials, Lagrangian interpolating polynomials are not necessarily sort of perpendicular to each other. And then you can actually go back and forth between these two representations using some kind of a transform. And this transform actually can be carried out by using a very simple linear algebra operation. It's basically just a matrix vector multiplication. That's called the Vandermonde matrix V, right? This Vandermonde matrix V allows you to actually to go from, for example, the coefficients of the modal representation u hat to coefficients of the nodal representation, which is actually the function value u at those special points, interpolating points, right? If you do this kind of matrix multiplication. matrix vector multiplication. And then if you actually stick this representation back into, say, this formula, right? So that replaces u ri with v times u hat, right? And then uh, both sides has to equal to each other, right? And then the representation has to be unique because Pn wiggle is kind of also normal. So you had cancels out on both sides of the equation. Eventually, you end up with v transpose times L has to equals to the Lagrange polynomial, right, as a vector. Um, and uh, and then if you actually so that also gives you some kind of relation between the Lagrangian polynomial and the Lagrange polynomial, right? It's basically just multiplying with the transpose of the Vandermonde matrix. And then how the Vandermonde matrix is actually defined, right? It's defined this way. It's basically just the uh, values of the Lagrange polynomial, right? Um, values of different orders of a Lagrange polynomial at those interpolating points, right? And then how do you actually get those values, right? So you need some way to actually compute the Lagrange polynomial, and that's what the codes are for. So I've been working on this particular class called Jacobi polynomial. No, that's this particular class. That's this Jacobi poly class, right? And then so Jacobi P allows you to actually compute the values of a Jacobi polynomial, right? What's the relation between Jacobi polynomial and the Lagrange polynomial, right? So Jacobi polynomial is some kind of a generalization of the Lagrange polynomial. So you've got two inputs here, alpha and beta. So when alpha equals to 0 and beta equals to 0, what you're getting is the Jacobi polynomial becomes identical to Lagrange polynomial. So if you stick alpha equal to 0 and beta equal to 0 into this into this particular function, then the output is going to be the value of the Jacobi polynomial at the location of the values inside of this x vector, right? And that's a function for computing the values of Lagrange polynomials, right? And in order to actually compute this particular Jacobi polynomial, we have to use gamma functions. And the gamma functions are provided in C++ by T gamma function, right? So it's a function in CMath, in the CMath library. So as long as we actually use the correct function, then the calculation of the Jacobi polynomial is quite straightforward. It doesn't actually involve too much of a complexity. It's just copying over existing formulas that you can find on the internet. It's not too hard, right? So once we know how to evaluate the Jacobi polynomials, we know how to evaluate Lagrange polynomials, and so basically we can test it out, right? So Jacobi p.txt, that's sort of the output of the Jacobi polynomial, right? And then x is sort of the input. The input here, it's a test code for testing the various functions inside of my Jacobi poly class. So suppose so the vector x goes from -1 to 1 with 100 points, and then I'm calling this function, right, with alpha and beta and n. That's kind of gathered from the command line inputs. And then it's going to write out a Jacobi p.txt output file, and then this output file has the shape of the polynomial. Suppose we call this particular function, right, with alpha equal to 0, beta equal to 0, and I want to know what's actually the zeroth order, right? Oh, too bad, I got something wrong with the first orders. Let me see. So the first order should be correct, right? So I'm gonna check out this problem later on. So let me just take a look at what's actually the Jacobi poly. So P equals to load jacobi poly, right? And then the first column and then the second column, right? Okay, so it's basically just a line, right? It's just a straight line. But if I do this a second order Lagrange polynomial, right? And then I'm gonna get what? I'm gonna hold on to the okay, it's more like a second order quadratic function, right? And then if I do third order, right? Right, sort of more complexities to it, right? And then fourth order, and then fifth order, right? So that's sort of the shape of the different orders of Lagrange polynomials from -1 to 1, right? Um, it's supposed to be identical to Lagrange polynomials. If I look at the Wikipedia, it's supposed to give me the same kind of figure, right? So if I just look at that, is that similar? I think so, right? It's okay. So zeroth order was like having problems, but I'll check on that. But um, first order is at -1 or 1. Okay, so for some reason the normalization seems to have a bit of problem. I don't really know why, but I'll check on that later on. It's supposed to be identical, right? It's supposed to be identical. Um, and then that's for computing the polynomials, right? For computing the shape of the polynomials. Um, and another issue is about how to actually select the locations of the interpolating points. And it turns out the locations, it's a bad idea to actually use uniform distributed sampling points. It's actually better to use the so-called Lagrange-Gauss-Lobato quadrature points. It's sometimes it's called Gauss-Lagrange-Lobato quadrature point or GLL points. Right? Here it's called ALGL points, and so so those kind of points are kind of selected based upon minimizing a certain kind of condition number of the Vandermonde matrix. So you don't want this kind of the condition number of the Vandermonde matrix to be kind of huge, right? So you want this kind of transformation matrix to have good quality, good conditions, good condition numbers, right? Because sometimes you may have to actually take the inverse of it. So um, and 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 in order to actually compute those points, we have another function for doing that. We have another function just for doing that. It's called Jacobi GL, and this Jacobi GL function actually calls Jacobi GQ function. Um, so the Jacobi GQ function is for computing the Gauss quadrature points for doing numerical integration, and um, and this function has to use a eigenvalue decomposition. So I have another class called eigen EIG, and then this function is kind of a The implementation still needs more testing. I'm not exactly sure if I actually got the implementation completely right. Um, it's it's again some code that I found on the web, and then I changed uh, the formatting of it to actually make it to work with vector of doubles. So the function that I was calling is actually this function, right? And then it's converted from this guy's code. It's based upon a technique called jacobi iterations, and I tried a few example matrix, and it worked out fine, but I haven't actually done extensive testing of this piece of code. Maybe I changed it. Maybe it's there are mistakes in my changes, but maybe there are mistakes in the original code. I'm not exactly sure, but so far so good. It works fine for my purposes. Uh, and it doesn't have to do this kind of the algorithm doesn't have to actually depend upon eigenvalue decomposition. There's also techniques for finding the roots of polynomials based upon Newton's method, right? But here it's actually trying to actually solve an eigenvalue problem. And then Jacobi GO is going to call that function. So Jacobi GQ function, and in order to actually produce the GOL points, right? So if you look at the GOL points, it's just right. So -1 and 1 is actually included in the two endpoints of the interval is actually included in the sampling point, and then the distribution of the sampling points is uneven, right? So it's not a uniform distribution over the sampling interval. So if I do like 20 points, right? And then it's gonna give me like 20 sampling points. WC that cache gl.txt 21, right? 21, because you also have a sampling point that's kind of in the center. That's 0, right? Um, Again, there are more data points close to the boundaries, and then the uniformly distributed sampling points. So that's a function for computing the sampling points Ri. So the sampling points CR equal to R are GOL points, right? Quadrature points. And then how do you actually compute the Vandermonde matrix V, right? So in order to actually do this kind of conversion from nodal representation to modal representation, right? There's another function for doing that, right? Inside of this, it's called a Vandermonde 1D. But once you have the Jacobi polynomial function, it's not too hard to actually compute the Vandermonde matrix, right? And it's just using this particular formula, just call the for the ith row jth column, you just the jth Lagrange polynomial with Ri as the input, right? But Ri now is actually the ith GOL points, quadrature points, right? Ith GOL quadrature point, right? Just stick that in there, and then you get the Vandermonde 1D matrix. And this matrix has good properties. So for this particular test code, I have v1d.txt. That's the Vandermonde matrix, right? So if I do a cat v1d.txt, then that's the 10 by 10 matrix. 10 by 10 matrix is kind of too long, right? Maybe let's 20 by 20. So let's do a 5 by 5, and then do a. That's gonna be a 6 row 6 column, 6 row 6 column, right? 1, 2, 3, 4, 5, 6, 6 row and 6 column. That's the V1 V matrix. Okay, so that's how to represent the function itself. Right? So if I have some kind of one-dimensional function, say the topography of a certain interface, if I represent it as a one-dimensional line, right? So the interface doesn't actually change in a certain direction, say y direction, then I can represent it as a one-dimensional line, right? And then the topography of that interface can be parameterized using this technique, right? And then we can sort of think about how to actually evaluate the derivatives of that particular one-dimensional function. It's the derivatives of that one-dimensional function is useful when we try to actually uh, come up with some kind of regularization schemes. For example, if we want to sort of make our interface as smooth as possible, right? So in that case, we can actually minimize the derivative of that one-dimensional function, right? So how do we actually represent its derivatives? In fact, the derivatives can also be represented as a matrix vector multiplication. So uh, so how it's done, right? How it's done? It's um, so the derivative is where is that? Okay, so that's the equation, right? So basically, that's the value of the function at a bunch of sampling points, and those sampling points could be GLL points, right? Um, and then that's a vector, and then you multiply dr onto it. That's a matrix, right? And then what you're actually getting as an output is actually the derivative of the u function at those sampling points. Could be GLL points, right? So the problem is how to actually construct a dr, right? And it's giving us a formula about how to actually construct a dr. It's constructed by multiplying Vr with the inverse of V, and V is the Van der Monde matrix. You just take the inverse of it and then multiply with the Vr. And what exactly is Vr, right? Uh, Vr is actually um, the derivative of the Van der Monde matrix. So it's generated using this particular method function, grad Van der Monde 1D, right? And in our case, it's just I was trying to find uh, definition of VR. So VR is derivatives of the jth order Lagrange polynomial evaluated at the location of the ith sampling point, right, which could be a GLL point, right? So in order to actually construct a VR, all we need to do is the capability to evaluate the derivatives of Lagrange polynomials, and we have this very nice property for Lagrange polynomials. It's a um, you see, so the derivative of nth order Lagrange polynomial actually equals to n subtract one's. It's not exactly Lagrange polynomial anymore. It's a Jacobi polynomial because alpha and beta is no longer zero. It's 1 and 1, right? And then all you have to do is to multiply the constant in front of it. That's how do you actually evaluate the derivatives. So in order to do that, all we need is a function to compute the derivatives of the Jacobi polynomials, and that's called the grad Jacobi. So grad Jacobi P allows us to actually compute the derivatives of a Jacobi polynomial. Right. Again, it has to call the Jacobi P. Right. Um, so once we have grad Jacobi P, we can actually compute VR. That's the grad Van der Monde matrix. Right, grad Van der Monde matrix, Van der Monde 1D. Yeah, that's DVR, right? DVR. So once we have both functions, all we need is another function to compute the inverse of the V matrix. Here we have a matinf. This inverse matrix in routine was based upon Gauss elimination. So that's a function that I grabbed from the internet. It's based upon Gaussian elimination, so it's not so efficient. But for our purposes, the matrix is like quite small. It's like let's say like a 100 by 100. So Gaussian elimination still works. So all we have to do is to actually call this particular function to actually get the inverse of of the Van der Monde function. Right? Once we got the inverse, all we have to do is to multiply them together. VR is like the the, the derivative of the ground, right? So multiply them together, then that's the derivative matrix, D matrix, right? So once we got the derivative matrix, we can get the derivative, of the function, right? We can get the derivative of the function at those points, at those interpolating points, right? And then the last thing we're gonna need is actually a implementation for the Lagrange interpolation, right? This is the interpolation function, right? If you stick like a one interpolating location, then it's gonna spit out the value of that function based upon the Lagrange interpolating formula. So we've got like a overloaded the interpolated function. So if you stick in like a one number, then it's gonna give you one number as output. But if you stick in like a one vector, then it's gonna spit out a vector, right? That's the interpolated value of the function at all those input locations. And then if I can test it out as here I'm using this particular function as the input, right? It's the same function that's used in here. That's this particular function, exponential sine pi x, right? The derivative of this function can be evaluated analytically, so it's just pi times cosine pi x times exp sine pi x, right? So we can actually compare the discrete derivative with the analytic derivative and find out how large the area actually is. So here I'm actually so I have a GAO points, right? I've created all the GAO interpolating points by calling Jacobi GAO here. So basically I'm trying to come up with some kind of a fake value, not exactly fake value, but the value of the function at the GAO sampling points, right? And then I can interpolate the function onto a uniform sample grid. That's X, right? X has like 100 points from -1 to 1. And then I can also come up with the derivative of this particular function based upon this derivative matrix, right? So here I have computed the derivative matrix, and then I do a matrix vector multiplication between this derivative matrix, and the U value. U is actually the function value on the sampling points, on the GAO sampling points. So the output of this matrix vector multiplication is going to be a vector that represents the derivative of the exponential function at the GAO sampling points. And then all I did was to do an interpolation of that function onto this uniform grid. And then it's written into a FDF text file. So so what I can do is to load the FDF file, right? FDF file, that's D1, right? I can actually read this particular file. Oh, I have to. This is for how many points? I can't remember. It's let me try to construct another figure, and then let me just plot it. Looks like oh, sorry. Okay, so that's my interpolated function using Lagrange interpolation, and then the GAO, the values of the function at the GAO points. If I hold on to that and then plot x, y, r, that's the original representation of the analytic function, right? The analytic function for this particular exponential function with uniform sample, right? From 100 uniform samples from -1 to 1. So it looks quite different, right? That's because we only have like 5 different points, right? We only use like 5 different points. But if I increase it to like 10, right? So the approximation is supposed to get better, right? this time let's use blue color. Right. So the blue color, the blue curve now has more accuracy, right? And then if I increase 10 points to like 20 points, then the accuracy is even better, right? So, right. So now um, the function almost has no difference with the analytic expression. We can actually quantify the L2 error and then plot the numbers, right? But here there's no need for that. What about the derivatives? This is the function itself, right? What about the derivatives, right? So the third column is actually the derivative. That's the derivative, right? Again, it's interpolated from the derivative values at those 20 GOL sampling points, right? But what about the analytic derivative, right? The analytic derivative was computed using this particular gradient function. It's not exactly analytic, but it's a numerical differentiation on a really dense grid. So it should still work, right? X, or maybe dy. Oh no, dy can be actually computed directly by using the analytic formula. So dy is going to equal to, right, and then so this is actually the analytic derivative evaluated at those 100 uniformly distributed sampling points inside of the x, right? So if I plot x dy with red color, then again matches, right? So the derivative also matches. Yeah, that's how we can actually use Jacobi polynomials and also the GLL interpolating points to actually represent a function through interpolation, right? And also the derivatives of functions through interpolation, right? Yeah, that's this video.